I'm professor at the University of Manchester and is a worthy inheritor and sustainer of this country's tradition in continuum mechanics. His work on free boundary problems has spanned from surfactant flows to plant root growth and extensive work in the area of his talk, namely flexible channels. So thank you, Oliver.
Thank you, John, and thank you very much for the opportunity to talk to you today. Yes, my topic is slamming in flexible channel flows, and as John just pointed out, I might be slightly abusing that word because it is used in the water wave community. This is a variant on that theme. So I should also acknowledge my co-workers here. Much of what I'm talking about is work by a former PhD student, Feng Shu, and I'll also touch on work done by Peter Stewart, who's sitting at the back, when he was in Nottingham, and also Matthias Heil in Manchester, John Billingham, who contributed at various times. The topic is an old one in physiological fluid mechanics, about a century old, which comes from work by the famous physiologist Ernest Starling, who built a contraption to understand venous return to the heart, and one of the bits of that contraption included a piece of rubber tube that was externally pressurized. And it turns out, and he was trying to use this as a resistor to try to provide some flow resistance by regulating the external pressure, but it's not a very good resistor because it's a very unstable configuration. So here is a sort of blow up of a realization of the Starling resistor, and you can see when you pressurize it, the flow here, internal flow is from left to right, that it collapses at its downstream end. The tube is very compliant, you get quite vigorous flow structure interaction, and so you get some quite vigorous oscillations of this device. And there's been a lot of work to try to understand the origins and mechanisms of these oscillations. I'm going to talk today exclusively about a two-dimensional realization of this device. So we have a channel, we prescribe the inlet flux, we prescribe the outlet pressure, and then we stick a membrane, a flexible segment of membrane in one wall. So here's our free boundary, and we may choose to pressurize it externally, but there's opportunity for strong fluid structure interaction, and it's oscillations of this membrane coupled to the flow within the channel that I'll be talking about. Okay, so here, just to illustrate what can happen, is a simulation that Matthias Heil ran on his finite element package umflib. So he's solved full Navier-Stokes within the channel. He's got geometrically nonlinear shell theory on the membrane. It's a monolithic solver, carefully resolved. And this just shows how under suitable conditions you can start with a uniform state, but then oscillations will spontaneously grow. And they get to very large amplitude. And the slamming that I'm going to talk about really is this kind of spiky behavior here, which happens when the membrane comes quite close to the bottom wall. That's what we really want to understand, is this transient interaction between the membrane and the wall. So it touches on some of the issues we've heard about this morning, about whether or not it's possible for there to be contact, and what sort of physics governs that interaction. So let me show you a little video from these simulations. So just to show you what you're going to see, the top picture shows the pressure distribution. So in the simulations, in this example, we fix the pressure at the inlet and the outlet. So the pressure will always remain fixed up here at the inlet and the outlet. And then in the rigid segments, there's basically just a forwards and backwards flow. So the pressures are rather dull in these regions, but you'll see variations in the pressure in the flexible segment, which is here. So again, flows from left to right. The contours show pressure. You'll see instantaneous streamlines. Here is a marker showing the location of the midpoint of the membrane. And here is a image of the downstream velocity, just to show you what's going on. So let's see how that looks. Is that going? Sorry, try again. Why is that not playing? So what are the things you will see in a second? I think it's just decided to have a breather. Oh, good grief. Let me try again. Sorry about this. Here we are. We'll see 2 cycles of the oscillation. So here's the first one. You can see the membrane is getting close to the wall transiently. There's a very low pressure just as that happens, large pressure gradients. That creates quite a large disturbance that then propagates downstream. And then the membrane bounces back upwards, and you'll see it one more time. So you can see there's a lot of sort of disturbances, fluctuations in the pressure when the tube is open, and then it's sucked down about now, and then bounces up quite rapidly. One of the things you'll notice is that the pressure contours remain pretty much vertical, and actually there's a number of slices of the pressure distribution here, which shows that there's not a lot of cross-stream variation in the pressure, which is something that we can exploit. Okay, so here's a graph from that simulation, just to give you an idea of what's going on. Some snapshots of the membrane shape during the oscillation. It's quite obviously large amplitude. Here the pressure and flux at the downstream end. You can see it's quite spiky at that moment when there's almost complete constriction. And here's the path of the minimum constriction. So there's again quite a characteristic little spike at the moment when it gets close to the bottom wall. So it doesn't occlude completely, but it doesn't linger near the wall. Now, because that pressure variation across the channel is small, that suggests you might be able to get a lower order representation of this system. And indeed, we were able to do that with a cross-sectionally average model that I'll show you in a second. So instead of solving 2D Navier-Stokes, we solve a 1D PDE system. And you can find, this is work of Peter Stewart, you can find very similar looking oscillations with the 1D model. You can see, for example, that the disturbances that you get after this spiky behavior generate a sort of ringing, which persists for a while, which is slightly bigger in this example than here. But still, I think this agreement, although it's not absolutely quantitative, does mean that the 1D model is going to be a good way to understanding the physics of the problem. Okay, so let me just tell you how the 1D model works. You can't get a consistent, simple closure of Navier-Stokes, nice simple reduction. You have to make an assumption somewhere. So the assumption that we made is that the velocity profile always has some sort of self-similar form. And the obvious one to choose is a parabolic form. So we assume that the velocity profile, axial profile, is always parabolic, and then build up a theory from there. So we write it in terms of the volume flux Q and the channel width H, and we can write down mass and momentum conservation equations, which I'm sure you will all recognize. So we've got inertia in the problem, so we have unsteady and convective inertia here. We have the viscous term, because we've made this assumption about the profile, gives us a term minus Q over H squared here, with a coefficient R, which is an inverse Reynolds number. So small r means almost inviscid. And then there's a pressure gradient, which is set by the curvature gradients of the membrane. We also include, for convenience, a small external pressure gradient, which balances the pressure gradient that you would have if the channel were uniform. So Poiseuille flow has a linear pressure gradient, so we just take that pressure distribution and stick it outside the membrane, which means that there's a uniform state where the membrane is flat, which is just convenient. So that's responsible for this term here. It doesn't have a major impact on large amplitude behavior. And then the boundary conditions that I'll be focusing on mostly is prescribing the inlet flux and the outlet pressure, and of course pinning the membrane at either end. So the pressure term is written in terms of the value of the curvature of the membrane at its downstream end, and involves viscous losses and unsteady inertia of the fluid in the downstream column. So the parameters in the problem are a dimensionless tension, this inverse Reynolds number, and also it's important to worry about the length of this downstream segment. Okay, so when you solve the 1D model, again you see this sort of characteristic behavior where the membrane becomes, well, the channel becomes almost completely occluded over a very short time interval. And so here's a few sort of snapshots of the membrane shape as you get towards this near complete occlusion. The curvature gets very large, the flux is almost completely pinched off, and that's can be quite challenging to get your computations through this. But if you can, then you find that you get this vigorous response to this near occlusion, causing these rapid disturbances which decay before you get yet another one of these so-called slamming events. And it's really, this is what I want to get towards, is to try to understand what's causing this and how does the channel recover. You might think, I mean, from the talk this morning, for example, we were thinking about factors that might prevent or cause interfaces to touch. With a viscous flow, of course, lubrication theory suggests that you won't get finite time contact, but we're in an almost inviscid limit when viscous effects are very weak. And so the role of viscosity in this problem is much more subtle. So the things that I'd like to talk about then mostly, first of all, to say a little bit about how we've come to understand the onset of the instability in this problem from the near uniform state. And then I'll, at the end, talk about a little model which tries to explain what makes the membrane become occluded and then recover from that occlusion. So let me start with talking about the onset of instability. So this is a long-standing question, and there have been a number of different advances in recent years. And you find that the boundary conditions of the whole system are very important, and you get quite different behavior depending on whether you're driving the system with a fixed pressure drop or a fixed flux. Okay, so just to tell you very briefly, if you fix the inlet pressure, you find that the instability is, like in the video I showed you, the membrane has what we call a mode 1 distribution. It's basically got one hump, and it bounces in and out like this. And that inward and outward motion generates sloshing motion in the rigid segments up and downstream. If the pressure is prescribed upstream, and if the upstream segment is relatively short, so you don't have a lot of fluid inertia there, you can generate quite vigorous sloshing up and down here, more than down here, and that asymmetry is actually sufficient for the flow to extract energy from the mean pressure drop that's driving the system. So you can get a transfer from the mean flow to the oscillations by the difference in kinetic energy fluxes at the upstream and downstream ends. Okay, so this was sorted out in this 2D problem about a decade ago, and subsequently it's been extended to show that the mechanism also works in 3D. Okay, but I'm not talking about that case today. Okay, so when you prescribe the inlet flux instead of the inlet pressure, this mechanism is completely suppressed. Okay, so there must be some other mechanism that initiates the instability. So there has been work on that problem previously. First of all, numerical work, which shows that the primary oscillation is not mode 1 but mode 2, so with two humps. And there's been also some valiant attempts to try and understand the oscillations using interactive boundary layer theory. And while lots of interesting things emerged from that work, then there wasn't a sort of clear view of what initiated instabilities. And there's also quite a lot of experimental work on 3D systems, but rather limited data available for this 2D system. Okay, so if you prescribe the inlet flux, we can go back to the model I showed you and try to analyze that. It has a base state where the membrane is flat, so H equals 1 and Q equals 1, and you can do a straightforward linear stability analysis of that state. And you can find a variety of different ways that the system loses stability, sometimes through Hopf bifurcations to oscillations, sometimes through transcritical bifurcations to different steady states. We concentrated on a particular point in parameter space where both of those things happen at once. We found a point where you get a simultaneous Hopf and transcritical bifurcation. And that actually happens when the inverse Reynolds number is 0 and the tension takes a particular value which we call T20. So what you have there is a codimension 2 bifurcation with 2 zero eigenvalues, and that's really nice because you can then start understanding behavior in the neighborhood of that point just by expanding very carefully. And I will spare you a lot of the details and just show you the results of that. So we find the primary oscillation is mode 2, as you might expect. And once you move away from that point in bifurcation, in parameter space, you find you get Hopf bifurcations and transcritical bifurcations, and then all sorts of other things emerge from there. So this is just a little snapshot of the sort of things that can happen. So what I'm plotting here is a bifurcation diagram fixing the parameter R, the inverse Reynolds number, and varying the tension parameter. And here's the special value T20. So we're at finite R, we've moved away from that bifurcation point, and we're splitting up all these different bifurcation curves. So close to this point, here's a transcritical bifurcation, and here's a steady branch of solutions, and a branch of mode 2 form where the channel is dilated and then constricted emerges up here and then turns around through a saddle node bifurcation and bends back, and there's another branch with the opposite sign which bends back here. And then the uniform state is stable between these two bifurcations, but then there's a Hopf bifurcation here, and it turns out an unstable limit cycle emerges from the Hopf and then bashes into this steady solution, which is the saddle point at this point. So you get clearly you get onset of instability, and then the question is, okay, mathematically we can see there's an instability. Physically, what is causing it? Before I go on, I'll just say there are other solution branches as well, steady solution branches of mode 1 form. So let's just have a look at what happens around here. So you can find through this weakly nonlinear analysis by deriving amplitude equations and understanding the dynamics that you get these kind of pictures of phase portraits. So your uniform state is the fixed point in the middle, and then the two neighboring unstable steady states are the saddle points either side. That you can easily get oscillatory growth, which is basically driven by the fact that the nearby saddle points are divergently unstable. So this is a very sort of key and ubiquitous kind of mechanism that you get in these kinds of flows, with a very simple explanation, which simply comes from the Bernoulli effect. If I've got a channel with a flexible wall, and I fix the flux, and I make the channel slightly narrower, mass conservation suggests the flow is going to go faster. Bernoulli says the pressure is going to go down, and that lower pressure will make the constriction grow sort of narrow more. Okay, so you just get a divergent kind of instability, and I think that's what's causing the instability of these two saddle points. And then oscillations are basically drawn towards each saddle point and then pushed away, and this is how you can get this growing unstable oscillation. So that was the theory. When we actually went back to the PDEs of our 1D model and did a simulation, you found exactly the predicted behavior. You get growing oscillations driven basically by the nearby saddles, but then ultimately your system gets pushed away and it goes into this slamming behavior. Okay, so that although there's some interesting physics that drives the initial instability, let's try and talk about what happens later on once it gets to this more vigorous nonlinear state. Okay, so that's one insight we had for the flux-driven system, and I should have emphasized this is what happens when the downstream length is small. Okay, the downstream rigid channel is small. So the downstream rigid channel really isn't having a bearing on the dynamics here. There's one other case that we looked at when this downstream length becomes much larger. So let me just tell you about that before we get on to slamming. Okay, so we go through the same process. We go back to our 1D PDE system. It's got a uniform state where the membrane is flat and the flux is unity. We do a linear stability analysis, but now we account for the fact that downstream of the membrane is a long rigid channel, and there's a lot of fluid in that channel with a lot of inertia. So any disturbance has to push a lot of fluid around. So we find that when you account for this long downstream channel, an extra mode becomes available. So you have the eigenmode that we've just been using before with a two-humped disturbance, but another one becomes important, which has got the same wavelength, but only one hump. And the two modes are illustrated here. So here's my normal sine 2 pi x disturbance, mode 2 disturbance, where as the membrane bounces up and down, fluid underneath it will slosh backwards and forwards, but won't really cause much disturbance outside. But it's also possible to have this additional mode, which is a one-humped mode of the same wavelength, And that one hump mode will, of course, generate upstream and down, will generate sloshing, but only downstream because we're prescribing the flux upstream. Okay, so the instability that can arise in this case does so through an interaction between these two modes. Okay, so how does that happen? Well, first of all, the downstream mode is going to generate some sloshing down here. The one hump mode, sorry, will generate sloshing down here. The two hump mode, you don't expect to generate much sloshing, but as soon as you make it slightly asymmetric, of course it will. Okay, and a little bit of viscosity, for example, will make this slightly asymmetric and will therefore generate sloshing here. So you've got the two modes interacting through their effect on the downstream segment, and that's sufficient for them to start resonating with each other. So we find that there is a one-to-one resonance. Because these have the same wavelength, they have basically the same frequency, and you can get quite a powerful resonance which generates an instability. So we give this mode amplitude A, this mode amplitude B, and here's an expression for the downstream flux driven by changes in B and asymmetries arising due to, for example, viscous effects in A. So it's quite subtle to get the balances right, but you can derive amplitude equations, and again you can start investigating the dynamics. And it's an unusual bifurcation with 4 zero eigenvalues and 3 parameters. So a lot of rich behavior, and we've not been able to analyze it all completely. But here's the sort of basis of the expansion. You start with a flat membrane, and then you have your two modes and expand away. So what does that do to the dynamics? Well, rather like the picture I showed you before, you find again you have, as you vary tension for fixed Reynolds number, a region where the uniform state is stable, bounded either side by a Hopf and by a transcritical bifurcation, and again you get these two steady solution branches, and one of them has a saddle node bifurcation, a turning point. You'll see here's a new instability. You find now that the non-uniform state undergoes a Hopf bifurcation through this resonant interaction. And also the Hopf of the uniform state occurs much closer to the transcritical bifurcation and also has quite a different form to what we had before. So whereas previously the Hopf was further away and was strongly influenced by these two steady states, now what we find is that here you get a very different looking instability, and the limit cycles that emerge have a rather strange, unusual structure. Basically what we're plotting here is disturbance versus the rate of change of disturbance. So you will have a situation where the dynamics is slow and then very fast, or equivalently you get a kind of sawtooth profile in the disturbances. So that suggests that the instability will have a rather characteristic rapid opening and slow closing. So don't forget, this was all done with a 1D model. Okay, so it's a slightly ad hoc model, and we've put a lot of effort into understanding it, and you could say, well, why put so much effort into a model that maybe is on slightly shaky foundations? Well, we were very pleased that this prediction was actually confirmed when we tried to solve the full 2D Navier-Stokes system in the neighborhood of a point such as this. Okay, so here are simulations from the 2D Navier-Stokes solver, which reveal this sawtooth type behavior. My machine cooperates. So again, the phase portrait, this is of the membrane height a quarter of the way along the channel, and you can see you have the slow, fast dynamics, and this should be evident. The flow is from left to right. The contours are showing the axial component of velocity, and you will just see the membrane in this segment here, and you'll see it slow to close and fast to open. Okay, so that gives us confidence that the 1D model captures a lot of the relevant physics of the 2D system. Okay, so in this case, the oscillation actually remains bounded. So again, that was a rather long preamble towards slamming. I hope that it gives you some confidence in the 1D model as a tool for investigating this 2D problem. Okay. So here's another bifurcation diagram for our inverse Reynolds number of 0.02. So we're a little bit further away from that special bifurcation point. And there's been some reorganization of the solution branches. The uniform state here still has a small range of stability, and we understand this hop, this transcritical and this hop. This is all well understood from what we were doing before. The uniform state is also stable if the tension is large enough, as you might expect, and actually loses stability to a non-uniform mode as the tension is reduced. So you can ask what happens, for example, if you look at the dynamics in this kind of region. We're miles away from these hop bifurcations. Is anything interesting going to happen? And yes, of course it is. It's going to slam. Okay, so the uniform state is divergently unstable. There's one real eigenvalue that pushes the disturbances away from this uniform state, and what it does, it goes off into a large amplitude oscillations with vigorous slamming kind of powering each reopening. So that's what we want to understand. And here is a little snapshot of that oscillation from the 1D model. And you can see that the vigorous kick leads to disturbances, bang, and then wobble, bang, and wobble. So what we want, this is what you're seeing here, of course, is the membrane shape. Take a couple of derivatives to look at the pressure distributions, and that starts to get quite steep here. And so we've really not, there's a lot more could be done to try and get closer to much more singular behavior. So what about the physics of that process when the membrane gets very close to the opposite wall? So we a few years ago with Peter, we wrote down a very simple model of what we think happens when you get this kind of slamming behavior. So you imagine that there's a region where the channel is highly constricted over a short region in space and a short region in time, and just ask what's the basic physical balance. What you can propose is that the pressure is basically uniform upstream and uniform downstream of the constriction, so that the shapes of the membranes are just parabolas, and there's something very interesting happening at the constriction. But then in this region here, where you have a parabola, the pressure in the fluid will be related to the curvature of the membrane, and as the pressure falls, this membrane gets more tightly curved, and the constriction will move further downstream. Now, if a constriction forms, that will basically cut off flow through the constriction, but you've still got a big column of fluid moving downwards. So suddenly you've got a situation where you've got fluid that wants to move downstream, but it's being pinched off at its inlet. That creates a suction on the membrane, and that suction should be enough to stop the fluid from going downstream and start to pull it backwards, and that should reopen the membrane. And that's what our little model was able to characterize simply on those assumptions I was telling you about. So parabolic membrane shape down here, where the curvature is related to the pressure. Mass conservation, which basically says that as the membrane gets more curved, this point must move further downstream. And therefore the rate at which this point moves downstream will be related to the flux of fluid in the downstream channel. And then you have to account for pressure drop across the channel, rigid channel here, which is either through unsteady inertia or possibly through viscous effects. And that little model produces a second order ODE, and you can sort of mimic the system, think of the system basically as a nonlinear oscillator where you have a dominant balance between inertia of the fluid in this column here and elasticity being provided by the membrane. So there's a kind of spring which means the downstream column is decelerated and then can recover. So it's very crude, a sort of ad hoc model, a toy model, but it's, it does get some of the very basic physics for how the constriction moves downstream and then upstream, how the flux falls and recovers, and how the pressure gets low and then recovers. Of course, what it doesn't do is tell you anything about how narrow the channel might get at the constriction, for example. And it isn't rationally based. So we tried to do something a little bit better more recently. So we go back to our one-dimensional model to see if we can find a consistent limit of that model. And to do this, we've rescaled some of the parameters. So we've got our inverse Reynolds number R, which is going to be our small parameter, which we will take to 0. And then we rescale the membrane tension and the length to give interesting balances. So that's the system I showed you before: mass conservation, momentum conservation, fixed flux at the inlet and fixed pressure at the outlet. We can supplement this by the corresponding energy equation. So you can derive an energy equation from these PDEs, and you have a number of different terms. I'll just point out a rate of change of kinetic energy, viscous dissipation, rate of working of pressure at the inlet, and so on. This turns out to be useful later on. Okay, so again, we're going to take the same approach. We're going to imagine that you can find a three-region asymptotic description of the channel when you have this transient severe constriction. And again, going to suppose that the pressure is uniform in the upstream and the downstream parts of the channel, but of course there's going to be a big pressure change across the constriction. So that means, again, you get parabolic membrane shapes, so very simple algebraic expressions for the shape of the membrane. At the downstream end, for example, you can find that the curvature of the membrane is related to the pressure losses across the rigid segment arising from acceleration or deceleration of that fluid column. So some quite simple expressions. This is one that I found quite surprising when we first came across it, that when you look at the constriction here, you might think that this is very narrow and viscosity should be becoming important here. But it's not. Okay, so the dominant balance we find here is between inertia and tension. So basically, the little ODE you get describing the membrane shape here describes a Bernoulli balance. You get a constriction that causes the flow to go very fast through the gap, that causes the pressure to be very low, and it's that pressure that balances the curvature. So it's an inertia tension balance at the constriction here. And we have to match the slopes of this little inner solution, which is symmetric to the parabolas either side. And we do something similar at the upstream end. Again, it looks messy, but it's just a parabola. Okay, so this is the system that you end up with. You have two mass conservation equations, flux in minus flux out equals rate of change of volume for the two big regions. You match the slopes across the constriction in the middle. You need one further condition to close the system, and the simplest way of getting that condition is, rather than going to higher order, is simply to use the energy budget, which is a bit of a mess, but this is what it is. And you can see terms in here, for example, the rate of change of kinetic energy of the fluid in the downstream segment. That's dominant because that segment is very long. And here is the viscous dissipation at the constriction. So the dominant viscous dissipation does happen at the constriction, but viscosity does not affect the shape of the membrane there. So this looks unpleasant. What we find is that when the constriction gets very close to the downstream end of the channel, a few terms become dominant. So particularly these two energy terms become dominant. The upstream conditions then become basically irrelevant, which explains why slamming occurs both for pressure and flux-driven oscillations. So you can take that full model. It's basically a third-order ordinary differential equation system with some algebraic equations attached. Find steady solutions, look at their stability. So the dotted line are the predictions of the model for steady solutions, and the solid lines are steady solutions you can compute directly from the PDEs. And in the limit of the Reynolds number going to zero, the inverse Reynolds number going to zero, they work very well. So this is the location of the constriction. And so when the constriction is nearer the middle of the channel, you get a sort of V-shaped membrane. As it moves down towards the downstream end, you get this characteristic mode 2 shape. And we were hoping that we would be able to see evidence of a Hopf bifurcation, which had been seen in simulations about here, but that wasn't to be. But when we did a linear stability analysis, we found that both branches in the reduced model were always unstable, and we could predict the eigenvalues well, but there's no sign of a Hopf, okay, which is rather disappointing. However, we can go back to simulations of slamming, and we can ask how well does this simple model capture the instant of a slam. Okay, so this is an example of what we see. So the green curves are the constriction, for example, during a slamming event from the 1D PD system. So this is all being put into rescaled variables. So the constriction is actually very small, and it goes down and up. Here's the location of the constriction that moves downstream and then upstream. Here's the flux at the outlet, and here's the flux through the constriction, through the minimum. And then our third order reduced system, we just match to this by fixing the constriction location and the flux and its slope at this point, and then we just integrate forwards and backwards to see how well the reduced model captures the PDE model. And certainly it works better than the toy model we had before, and you can integrate backwards and it predicts these shapes rather pleasingly. Integrating forwards though, although the constriction seems to work nicely and this flux works nicely, we find that although it's not very clear here, that the minimum channel width and the constriction flux both seem to blow up in finite time. Okay, so we have evidence of a singularity in the reduced model, which may well be a signature of the rather sort of explosive event which is causing the channel to reopen rather abruptly. So to understand where that comes from, you can take that reduced model and ask what happens when the constriction gets very close to the downstream end. A lot of the algebraic complexity disappears. And what you can derive is again a nice second order ODE for the location of the constriction. A is a constant of integration, which really mimics the second order ODE we got in our toy model. This is the balance of the membrane and the downstream inertia being like a spring. This is what causes the constriction to move downstream, stop, and bounce back. But now we can also say something about the actual height of the constriction. We find that the height and the flux through the constriction are slave to each other by this Bernoulli effect. You know that how the constriction moves will tell you how the flux in the downstream segment will change. So in particular, when the constriction stops moving, that flux is going to stop when that's the moment of flow reversal downstream. And then the key observation comes from the dominant energy budget. We have the rate of change of kinetic energy in the downstream segment balancing viscous dissipation at the constriction. And you can probably see that initially the constriction is advancing, the downstream column is slowing down, so dq1 dt is negative, so you have a negative thing balancing a positive thing, that's fine, but as soon as q1 goes to 0, this h00 will go up to infinity. So that explains the singularity. There's a nice balance of energies, non-local, in the dissipation at one region balances the rate of change of kinetic energy somewhere else. But as soon as that balance breaks down, the system has to violently readjust. And so that, we think, is the mechanism that gives the kick that reopens the membrane. So one curious thing about this is that you might think this might be a purely inviscid mechanism, for example, where at a high Reynolds number, maybe we can neglect friction completely. That's certainly not the case. Friction does not affect the shape of the membrane, it only affects the dominant site of dissipation, but it does seem to regulate the dynamics quite profoundly. Okay, so let me just summarize what we found here. First of all, I hope that these results have convinced you that although it's slightly ad hoc, the one-dimensional model has been or can be very useful in understanding a much more complicated 2D system. We've been able to do that by analyzing the 1D model carefully and then comparing to 2D simulations. And at least qualitatively, we can recover slamming behavior and these sawtooth oscillations and so on. There are a number of different mechanisms causing the onset of instability, and these are very sensitive to the inlet boundary conditions, whether you prescribe the pressure or the flux. And if you prescribe the flux, then there's different mechanisms that we found depending on the length of the downstream segment. So this is a very much a global problem. And we found that there's either a mechanism which involves a divergent instability of two nearby steady states or a resonant interaction. Slamming appears fairly ubiquitously in these two-dimensional channel flows, both in 2D simulations in the 1D model and irrespective of the inlet boundary conditions. And it does seem that it provides quite a vigorous kick to each oscillation, which generates a kind of ringing disturbance which settles down, and then you get, again, this divergent instability into a slam and then a kick out of it. We can rationalize that behavior by showing that the membrane and the downstream fluid column basically have the elasticity and the inertia of a nonlinear spring. But you have to use an energy argument to understand how that breaks down, so that the dissipation at the constriction can suddenly no longer balance the kinetic energy that's being burnt up by the deceleration, and the system adjusts rapidly. So that's the story. Thank you for listening.
All other questions? Timothy.
A comment really, and leading to two comments leading to a question. First of all, it's very impressive to me this your 1D model, which has led, unlike the previous valiant models that you referred to finite amplitude self-excited oscillations. And the key difference, it seems to me, and you can comment on this, is the fact that in your 1D model, the resistance term, what you call the inverse Reynolds number, the resistance isn't identically zero. It's got to be there. And then you can get your instabilities, which can lead to finite amplitude oscillation. I think that's but all that work that you and Stuart and Shu and everybody have done is really has really taken us a long way. It's great. Now, and it's all partly, you could say, it's based on the very useful and interesting device of adjusting the external pressure so that the basic state is parallel, and then you can do small perturbation analyses and all that sort of stuff in a rational way. Of course, previous Navier-Stokes computations, as you know, didn't do that, so that when and the external pressure was a uniform quantity which could be raised, for example. When it's raised, then the steady state is one with significant indentation already. And that's, of course, rather more difficult to analyze. So my question is, now you've sorted out this parallel 1D model in so much detail, can you does this lead to more insight in what's going to happen, A, when you've got finite indentation, and B, while I'm at it, in a 3D tube?
So to answer your first question, yes, there's a symmetry in our system which is not generic. Okay, because our base state is flat, we have transcritical bifurcations as the primary static bifurcation. And of course, if you break the symmetry with external pressure, that will break up into pairs of saddle nodes or into disconnected solution brushes, which is something I think some of the work that Julie Gunnar-Ratner did, for example, showed that kind of behavior. So we can certainly start attacking that simply by perturbing the system that we have at small amplitudes. Once you go to large amplitudes, anything can happen, I'm sure. And I really don't know to what degree the mechanisms that we found here will persist once your base state is very non-uniform. That's an interesting question.
I mean, if you get slamming, then your model should do slamming.
Yes, I expect it to slam, but it may well be that the onset mechanisms are different. Whether you get resonances or whatever. 3D, oh heavens. The 2D system, of course, is very special because the constriction completely stops the flow, and in a 3D tube you have regions either side where the flow can go around the edge. So it's really hard to say on the face of it whether this mechanism will work. However, the experiments that have been done on the 3D system do often show a very vigorous kick. So one hopes there might be some connection.
Lubrication theory, with these thin gaps, you often get cavitation. Can this happen here?
That's an interesting thought.
Well, I mean, do people who look at blood flow, do they see bubbles when this sort of thing is happening?
I'm not aware of anybody reporting it, but it's
So it might be worth just checking.
Yeah.
How low could the pressures get?
avoid constricting your blood vessels when you're doing deep sea diving.
Well, that's we've got one or two experts on the subject here, haven't we, James? Just seems to me, if you have the pressure too low, it is going to count.
Yes, no, I can see that might be possible. Yeah. Interesting.
So your penultimate slide, does that lead to a power law for blow up or something?
Does it lead to?
Power law blow up or something?
Yes, there's a 1 upon T blow up in the constriction, but that's because we've missed some physics. So I think there's that basic singularity in the system, and of course it's regularized by other physics. But it's nice to think that singularity is what's providing the kick.
But it always tell you how to rescale to get a different balance, right?
Yeah. Yeah.
Any other questions from them? If not, can we thank him for a lovely combination of mathematics and physical insight? Thank you.